Mr. Chairman. Today I talk about under this title, and I'm afraid it's a little bit different field from what was going on this symposium. I'm talking about just fundamental and maybe applied to the future display devices, or we are interested in a little bit different field, switching or modulation area. But anyway, I talk first, after brief introduction, I talk about materials, and then talk about how to use these properties of these polymers for all optical information processing. First, today I had a long way to be here because Kyushu and well, especially Fukuoka and Busan is very close. It takes about only 15 minutes by plane, but I don't know the reason. Direct flight from Fukuoka to Busan was full for more than 1 month. So I decided to use SIP to be here. But suddenly, yesterday afternoon, all SIPs were cancelled today due to very strong wind. So the only way I will be here is to take a long way. So this morning I went to Kansai, which is located in Osaka area, and came back to Busan. It takes about 5.5 hours. Okay, anyway, Kyushu University is started to move. Originally, it was the east part of this Fukuoka city, and we moved to the west end of Fukuoka city, and this is a view from our building. You see the Fukuoka Tower, it's a ballpark, big ballpark around here. And this is a picture of a new building. So last year, half of the faculty of engineering moved, and the other half will move this October. So these are this is a total picture of the new buildings for faculty of engineering. So chemistry department is located in this area. Okay, so before I talk main topics today, I talk about some results on information processing. Probably all of you know what is needed for information processing. First, conversion from optical to electric, or from thermal to electric, or anyway. And it's transportation and storage and creation and modulation switching, and so finally it's man-machine interface. Its display is very, very important field. And so the topic in this symposium is mostly related to the display. There are many advances, great advances in the emissive and non-emissive, as you know. But to achieve high performance in any area of this information processing, we need fundamental chemical or physical studies, as well as device structure and processing. So the main theme I talk today is this fundamental research. And recently, organic semiconductors or organic transistors are very popular, and to achieve such a high performance organic transistors, we need information on what is going on in this organic layer. So we did probably this is the first result at the same in about 10 years ago. At that time, German and British people, as well as our group, has studied the transient response of these well-ordered organic, very thin layers, and we demonstrated pi electron system is much more efficient to carry the photogenerated carrier in this case, which are generated by these porphyrin derivatives. And we later actually determine the decay constant by using a conductive atomic force microscopy. This is the example. And another example for practical, important point for practical use is solid properties or thermal stability of thin film, especially thin film, thin polymer film. And we have been making a lot of work on this surface or bulk properties of very thin films. In this case, I plotted the gas transition temperature of polystyrene as a function of molecular weight, and for the surface area and bulk area. So the gas transition temperature is remarkably depending on which area we see. So that surface area is gas transition temperature is very low as compared with the bulk area. So which means the surface is more active or more dynamic as compared with the bulk area. So this is very important for making polymer thin films as any kind of devices, solid devices. It is essential to know the thermal properties of this ultra thin film. So we invented scanning viscoelastic microscopy, and we added a sinusoidal pulse to the surface, and we detected this response as a function of temperature and the frequency. So this example. And recently, we are making another way by using a non-contact method. This is using optical excitation to see the molecular motion in such ultra thin films. And I show you only one example. So these figures show schematically. This very big one presents a thick film, it's a bulk film, and a thinner one and the thinnest one. So depending on the thickness, the molecular motion is dramatically changed as shown here. So by decreasing the thickness, the molecular motion becomes very, very rapid as shown in this. This is a fluorescence decay curve, so from which we can get the information on the mobility of this polymer chain in these areas. So actually we are now analyzing using a two-phase model, or in some cases three-phase model, surface, bulk, and interface. So all these areas show the different thermal properties. So from now I talk the main topic I want to give you. It's a molecular photonics. Molecular photonics means we use the interaction of photons and molecules to achieve all kinds of information processing by the way of absorption or refractive index, the fluorescence, or nonlinear optical properties. And first I show you one example of color change, which may be used as it's a display device. So probably all of you know what is photochromism. Photochromism is a color change due to photoirradiation, which is caused by the change of chemical structures, ring opening, closure, or transist isomerization, and so on. This is a photochromism. And there's another chromic behavior which was used many years, about 20 or more years ago, as electrochromic display. And electrochromic display using inorganic materials, I think it's still in the market a little bit. So the electrochromism, as you know, is a phenomenon of color change due to the redox reactions. Okay, so the one electron addition or removal will change the electronic state of materials, which form the color state. And we combine these two phenomena. These are phenomenologically combined. The actual case is photo-induced electrochromism. So we control the electron state of molecules by photoirradiation, not chemical contact. So that is a photoinduced electrochromism. So these photoinduced electrochromism has many severe properties as compared with normal photochromism or electrochromism. Because time is limited, I a little bit skip the detail. And one thing I'd like to show you is that we can control the colored state or absorption spectral response range, wavelength range by, for example, in this case, we try to make absorption change in the optical telecommunication wavelength region, which is about 1200 to about 1600. So we have been making two approaches. One is change of the pi conjugation or extent of pi conjugation by simply adding or removing one electron. So if we introduce one electron, which is assisted by photon, then the pi electron system becomes large, which gives absorption in the near infrared region. And if we remove the pi electron system, the conjugation length becomes less, small, then this absorption will disappear. And another way, I don't have time to talk, but this is also the color change in the near infrared region by using interaction of two chromophores, which was did by Dr. Park, who is in the audience today. But I skip this one. So, as an example, I show you this polymer. This polymer contains a fluorine unit, which is very famous for electroluminescent device. It's a blue emitting compounds. And we introduced two units for pyridinium at 2 and 7 position of this fluorine. And we introduced this chromophore as a part of the main chain of polymer. So this polymer shown here, we can make a very high optically transparent and tough film, as shown here, which is very, very luminescent. The fluorescence quantum use is about 0.78. And if we irradiate, for example, this position, then the color change from bright yellow to brown color, as shown here. And then if we, in this case, because this is a cationic compound, so which needs a counter anion. So we used this tetraphenylborate as a counter anion. So in this case, this counter anion is known to be decomposed after electron transfer. So in this case, we can observe the steady state color change as shown here. So this brown color comes from the absorption in this visible region. And at the same time, you see the very strong absorption in the near infrared region from about 1000 to 2000 nanometer. And by studying electron spin resonance and other method, we concluded this near infrared absorption is due to the long axis transition of photogenerated species and this visible absorption to the short axis transition. So, which means this, before photoirradiation, these three units are not in a planar way, but after one electron is transferred from counter anion, it becomes totally flat, and which gives this absorption change. So then we change the counter anion as I minus, iodide. Then in this case, there is no steady state color change, but if we use a femtosecond laser, we can observe a very fast color change as shown here. This absorbance change as a function of time at 1380 nanometer. So by using 50 femtosecond laser. So in this case, very fast rise and pretty fast decay. So the electron is actually transferred from counter anion to this unit, and this pi electron expansion is actually occurred, but it rapidly returns electron to this counter anion. So only instantaneously we can observe this color change. But we can use this color change in the in the later section. So we have several compounds. For example, carbon nanotube, and we have been using metal nanorods, and it's a polymer, as I just told you. And we have several compounds. I also give you the example of that hydrogen in the later part. So in order to use such properties, we proposed a new method, as schematically shown here. This is very simple. We proposed this system about 10 years ago. This is a prism glass slide, which is covered with a metal film and polymer film. This polymer film contains dye dispersal as a part of the main chain. And if we introduce light from this direction, so at some condition, shown again here, if we introduce light from this direction, and at some condition, the reflectance becomes almost zero. So as schematically shown here, and this is actually observed data. And this is because of the formation of guided wave mode as shown here. So light is confined in this thin polymer film as schematically shown here. So the lateral dimension is a few micrometers. So light is confined here. So, but if we change the complex refractive index of this polymer layer by using this light, then the condition change, which is shown here, so which gives this reflection again. So we can change this condition by using this light. So we demonstrated by using several compounds. This is an example. This is a fulgide. Fulgide shows photochromic. This is due to change of the chemical bond. Okay. By using a blue light or green light, we can write and erase. This is an example of the pattern written in the laser beam. So by this blue light or green light, we can change absorption state of this fulgide molecule. Then we can change the condition as I just told you. So if we fix the incident angle, for example, here, then the reflectance becomes larger or smaller by the photochromism achieved by this compound. But this works very well. But this system has some problems. One big problem is metal thin film, as you know, can be evaporated or can be broken by using femtosecond laser. So that is a big problem. And this is not big, but metal film also has a large dispersion of complex refractive index. So in order to solve this problem, we very recently proposed a new way of optical control of reflectance by using only polymer, two kinds of polymers, which is shown here. Instead of metal thin film, we introduced the low refractive index polymer, which is we now using a commercial polymer produced by Asahi Glass Company, which is the commercial name of Cytop, which has about refractive index of about 1.34. It's very low refractive index polymer. And if we form thin layer of low refractive index and then form photoresponsive polymer shown here, then which is similar but very different as compared with metal type film. Larger, a relatively large incident angle, there is a very, very sharp decrease of reflectance as shown here. And this is also due to the formation of guided waveform, which is caused by interference of two lights coming and reflected. So the light is confined here. So this incoming light will not come out at this incident angle. And this condition is controlled by many factors. One is imaginary part of this polymer film and the real part of this polymer film. And this type of device has many advantages as compared with metal type, as told you before. In addition to the durability. So I'll briefly explain the reflectance as a function, the behavior of reflectance as a function of extinction coefficient. Extinction coefficient is this K. Okay, this corresponds to the absorption. So if we use a metal type, so the reflectance becomes larger if we increase the extinction coefficient, which in other words, if we increase the absorption of this polymer layer, the reflectance becomes larger. Okay. So if the absorption of this polymer layer is large, the reflected beam intensity becomes large. This is for metal type. But for the two polymer layer type or low refractive index type, first at very low or no absorption, the reflectance is 1. Okay, so which means the total reflectance. It's a bright light comes from here, but it decreases very sharply at a very low level of extinction coefficient, and it becomes minimum, almost 0. Then it increases again. And if we use this slide projector using just a filter of this type, okay, this is a transmission type, then of course as the transmittance becomes smaller at some value, and then it becomes very, very small at higher absorption, of course. So this behavior is totally different. So one of the most advantages of our system is sensitivity. Sensitivity means that we can control very small light intensity to control the very high, large change of reflectance by using this device. So we demonstrated, this is a structure of cytop, as I told you. So we demonstrated using this cytop as a low refractive index polymer and this polymer as a photoresponsive polymer. We actually observed this result was obtained by using a femtosecond white light, and these red, blue, and green curves was observed at different incident angles. So in this type, reflectance becomes smaller depending on the incident angle. But for the simple transmission type, of course, there is no such incident angle dependence, and the change is very small, as you can see. And we also, this is in the visible region, and we also demonstrated by using this phthalocyanin in the near infrared region from about 900 to 1600 nanometer region. So by using this phthalocyanin, which was dispersed in another polymer, so by which we made photoresponsive layer shown here. We also used cytop layer, and then we observed this guided wave mode by using this light. We actually, this is after 0 picosecond after excitation. So we, depending on the incident angle, we can tune the change of the reflectance as shown here. So I think I almost use the time. So this is a conclusion. So we are mainly interested in ultrafast photoresponsive materials and how to use it in optical processing. Oh, sorry. Maybe it's hard. So these works are made in Shizuoka University and also at the Kyushu University, where belong to this university. So thank you for your kind attention.